Hi, this is Mr. Bear, and we're going to be doing number 51. In number 51, it's asking you to calculate the molar solubility. Let's remember that molar solubility is moles per liter. So really, you're just looking for the molarity of the solution that's formed when your salt is dissolving. So the salt that they give you in question is silver bromide. Silver bromide's a solid, and as it dissolves, it's in equilibrium with the solution producing silver ions and bromide ions. This question's made really easy for you because there's only one silver ion and there's only one bromide ion. The question tells you that it's a pH of 7 for part A because it is indeed pure water. So to solve the problem, what you have to do is you have to go in the back of your book and look up the KSP, which is the solid product solubility constant for silver bromide. When I go to the back of the book, I discover that it's 5.0 times 10 to the negative 13th. Oop, make sure I write that 1 there. All right, now let's write out what KSP is. KSP is equal to the concentration of the silver ions times the concentration of the bromide ions, and it's to the power of their coefficients, but the coefficients are 1, so simply it's just the silver ions times the bromide ions, and there you go. That's your KSP. You don't divide it over the reactants because the reactant is solid, and remember we don't write out equilibrium expressions dealing with solids or liquids. So I'm going to solve this one backwards. 5.0 times 10 to the negative 13th is equal to the concentration of silver ions times bromide ions. Now the convenient thing is they're in a 1-to-1 ratio, meaning however many silver ions I have in my solution is equal to the number of bromide ions at the same time. So I can set that as a variable we'll call x. Since silver is x and bromide's x, it's x times x, which is x squared. So what you do is you obviously take the square root of your solubility product constant. So in my calculator, I do 5.0. Actually, don't even bother typing the 5.05 e negative 13, and then you want to take the square root of that. I always like to do to the power of 0.5, and then you end up with your answer, which is 7.071. And let me change that into sig fig. 7.07 times 10 to the negative 7. And that's your x. Now, since x is the concentration of silver and bromide, that is always in molarity. And since molar solubility is used in molarity, that right there is my answer. Continuing on with problem B, which is the same salt dissolving, which is silver bromide, but now they've given us a new salt. So again, it's silver bromide, and it is in equilibrium with the solution forming silver ions and bromide ions. But now they're telling you that you're adding in a solution that is 3.0 times 10 to the negative second molarity of silver nitrate. Now, silver nitrate is a strong electrolyte, meaning it totally dissociates. So this is actually breaking apart, and you have that concentration of silver ions and nitrate ions. Now let's look at this in terms of Le Chatelier's principle. If you look at it in terms of Le Chatelier's principle, if I have silver bromide that's dissolving in solution, let me draw a picture of this so it's a little bit more clear. I've got a beaker, I've got some AgBr on the bottom, and I've got my liquid here. What's happening is silver ions are dissolving, bromide ions are dissolving, but they're also going back and forth because there's this equilibrium that solid has with your solution. Now you're dumping in silver nitrate, AgNO3, and when you dump in silver nitrate, you're increasing the concentration of silver ions. Yeah, you add nitrate, but let's look at this equation. Since I add this, it means that this concentration goes up. Now, Le Chatelier's principle says that the reaction responds to stresses to lower the stress. Well, the stress is I've increased the amount of silver ions in my solution. Therefore, in equilibrium, it shifts this direction. It shifts to the left again, which means I have less silver bromide dissolved in my overall solution. So now I have to figure out what the concentration is. Again, I know my KSP. The KSP is the same from the back of the book as I looked it up before. And my KSP is, let's see here, 5.0 times 10 to the negative 13th. And that's going to be equal to the concentration of reactants times the concentration of the product or I mean, sorry, the concentration of the products, because we don't write the reactant since it is solid. Now here's where it gets really interesting, is that, remember before in the last problem, I put in x for each of those values. I'm not going to put in x for each of those values now. What I'm going to be putting in instead is, for silver, I'm going to be putting in x plus this number right here, which is the concentration of silver ions, because now my silver ion concentration is higher. So I'm going to rewrite it not as 3.0 times 10 to the negative second, I'm going to rewrite it as 0.03. And then bromide, I didn't increase the bromide concentration by adding silver nitrate, so it stays exactly the same as x. So now, of course, I have to solve for x. If you're looking at it going, uh-oh, quadratic time, don't worry about it. You don't have to do the quadratic. That's because x, when you add it to 0.03, is going to be a very, very, very small number. So because of that, this one, as we have in previous equilibrium questions, we can assume it's 0. The book will often write it like this. They will say that x plus 0.03 is pretty much, and they write it out like that, pretty much the same as 0.03. It doesn't change a whole lot. So, continuing the problem, what I'm going to write out is 5.0 times 10 to the negative 13 equals 0.03 times x. That's it now. So obviously I divide by 0.03 on each side. That goes away. And the concentration, the molar solubility, what I'm going to get is 5e negative 13 divided by 0.03, and I get my answer, which is 1.67. X equals 1.67 times 10 to the negative 11. And that's in molarity. And that's for both the silver ions and the bromide ions in my solution. And that right there is our molar solubility. Now, if you look at the next letter in this problem, it's going to be exactly the same type of math. The only difference is when you look at 53 or 51C, now we're increasing the bromide concentration. So it's essentially the reverse of what we just did. So let me write out how we do C. So this was B here. Let's look at C. So C, it's the same setup. The only difference is this time it's not the silver ions that we're adding to the concentration to. They stay X. It's the bromide ions. So it's X plus, what is it? It's 0.1 molar. So essentially these two problems are the reverse of each other. It's the same setup as A. The only difference is that you're adding a stress which shifts the equilibrium a little bit. And then of course you have to add that in to your solubility product expression. The other thing to keep in mind when you look at these typical questions is to remember this shift that I showed right here is called the common ion effect. So if I'm adding common ions for the salt, it shifts it back to the left. That's an important concept to understand. Now we're going to move on to question number 53. Number 53 is very similar in terms of what it's asking. So 53 says to calculate the solubility in grams per liter, and it's of manganese hydroxide, OH2. So it's a solid, and it's obviously dissolving and releasing manganese ions, Mn2+, and 2 hydroxide ions, both of these being aqueous. Now the question gives you pHs that you have to deal with. So the pH for the problem that you have to deal with, and I don't want to get into this quite yet. Hang on a second. Let me write KSP. Remember, I've got to look up the KSP for this like I did in the last problem. 1.6 times 10 to the negative 13th. I got that from the appendix in the back. I believe it's Appendix D. And it's going to be equal to Mn2+, concentration of manganese, times the concentration of hydroxide, but now I have to put it to the power of 2 because there's a coefficient in front. Now it's the same setup as last time. We're going to put in X here to figure out the concentrations. But the given information this time tells us that we're starting off with a particular pH. And the pH is 7. If the pH is 7, the pOH is also 7. Now here's the interesting thing when you have a pOH of 7. That means that there are a small amount of hydroxide ions in your solution. Let's look at this equilibrium expression one more time. If I have more hydroxide, that's going to shift it to the left. So we have to pay attention to the acidity of our solution, the pH of the solution, because it does affect our equilibrium expression. So if I have a pOH of 7, knowing that pOH is the negative log, that means that my hydroxide ion concentration in neutral water is actually 1 times 10 to the negative 7 molarity. So when I plug in numbers here, I know my manganese is X. My hydroxide ion concentration I know is 1.0 or 1.0 times 10 to the negative 7 molarity squared. So when I want to solve this problem, what I'm going to do is I'm going to solve for X using that equation right there. So when I solve for X using that equation right there, and be very, very careful with your calculator, because as I did it, I made a mistake actually, you end up with a concentration for X being about 16 molarity, believe it or not. But the question, remember in the very beginning, was asking for grams per liter, not molarity. So you're going to have to convert your molarity into grams per liter. The way that I like to do it is I take 16 moles per liter, and then I'm going to have to change the moles to grams. So I multiply it by a conversion factor, where I have grams on top, moles on bottom. And then this, of course, is going to be my molar mass for manganese hydroxide. And that molar mass ends up being 88.95 grams. When I do my conversion, I end up with grams per liter, which is what it was asking for, and that's 1.4 times 10 to the third grams per liter of manganese hydroxide. So if I wanted to do B, that was all A. I'm going to show B a lot faster this time. So for B on this particular problem, they tell you that the pH is 9.5, which means that the pOH is 4.5. When you do the anti-log of that, you figure out that the hydroxide ion concentration is actually 3.16 times 10 to the negative fifth. So I know KSP for this manganese hydroxide, remember it's MnOH2, oops, sorry, I have the 2 in the wrong spot, solid, in equilibrium with manganese ions and 2 hydroxide ions, okay? The KSP value, it's extremely important to remember, comes from the back of the book. That's not something you have to calculate. It's because it's a constant for a specific temperature for manganese hydroxide. So it's equal to X again for manganese. My hydroxide ion concentration is going to be 3.16 times 10 to the negative fifth. Then I have to solve for X in this equation right here, and I find that X is equal to 1.6 times 10 to the negative fourth. And then when you get that answer, that of course is in molarity, and you'll have to do the conversion like I showed you in A to change it into grams per liter. Now what I want to do is briefly go over number 55. Number 55 is asking, which of the following salts will be substantially more soluble in an acidic solution than in pure water? Well, when you have an acidic solution, the pH is below 7, which means you have more hydrogen ions in your solution. You have a higher concentration of hydrogen ions. So if I'm dissolving the very first one, which is A, zinc carbonate, the zinc carbonate solid is of course in equilibrium with its 2 ions, zinc 2 plus and CO3 2 minus. Well, if I have extra hydrogen ions in my solution, they are going to stick to the carbonate. Why? Because carbonate is a conjugate base to the weak acid hydrogen carbonate, which is otherwise known as carbonic acid. So if your salt has within it the conjugate base to a weak acid, if you decrease the pH, you'll dissolve more of the salt. I'll give you another example. Let's take a look at the salt on number 55. Let's take a look at E. All right, so E has Ba3PO4 This is the anion to a very weak acid, which is phosphoric acid. So, because of that, if you have a pH below 7, more of the barium phosphate will actually dissolve. So the correct answer for this question, the ones that have the conjugate bases to the weak acids, for number 55 are A, B, D, and E.